Okay, so this is the other examinable proof by contradiction. I think that says it all, doesn't it? So proof there are an infinite number of primes. So same idea, you suppose the opposite is true. So suppose there are a finite number of primes. And then next lesson you can have a go at doing some of these yourself of primes. So if there's a finite number of primes, you can list them. It could be a long list, but it will terminate. So we can talk about 2, 3, 5, 7, up to P. So this is the largest prime. And we're going to let Q equal 2 times 3 times 5 times all the primes together plus 1. And then we can consider whether Q is prime or not. So Q is either prime or it is not prime. So if Q is prime, then it is not on the original list. And job done, you've got a contradiction already because we've listed all the possible primes and we've found another one. So we don't have to do any work with that. The other option is that Q is not prime. So if Q is not prime, then it must have a prime factor. So it has another factor apart from 1 and Q, which is prime. None of the listed primes so i.e. 2, 3, 5 all the way up to P, can be a factor of Q. As when you divide by them, so when you divide Q by any of them, you get a remainder of 1. So because Q equals all of the primes multiplied together plus 1, if you divided Q, say, by 3, then you'll get 3 times all the rest multiplied together plus 1. So you've got this remainder of 1. And that's the same for all of them. So if Q is not prime, it must have a prime factor which is not on the list. That means there is another prime number not on the list. Which is not listed. And that is a contradiction because we've listed all of them. So therefore there can't be a finite number of primes. So not necessarily an obvious proof, but it's just one you're meant to know. So hopefully that all made sense. And then, yeah, next lesson we'll have a go at doing a few, but they won't be as hard as this, so don't worry.